Good afternoon, everyone. A very warm welcome to today's seminar. Today's talk is part of the Australian Institute of Physics Theoretical Physics Seminar Series for 2021. I'm David Tilbrook from the Department of Fundamental and Theoretical Physics at ANU, and I'm hosting this series of seminars on behalf of the AIP Theoretical Physics Group. I'd like to start by acknowledging the people of the Ngunnawal Nation, the traditional custodians of the lands upon which we are located here at ANU in Canberra. And of course, we also acknowledge the traditional owners of lands all around Australia. We'd like to pay our respects to their leaders, past, present, and emerging. I'd also like to acknowledge Murray Batchelor and the other members of the organising committee. This seminar is being organised by the Theoretical Physics Group within the AIP. And the organising committee has done a lot of hard work to ensure that we have great topics for discussion and great lecturers. You are most welcome to join the Theoretical Physics Group of the AIP. If you'd like to do that, it's free, of course, to members of the AIP. Just log into your AIP webpage and you'll see that the Theoretical Physics Topics group there, and you can just click on that to join. So far in this series of talks, we've had seminars on a range of topics such as dark matter, the G2 experiment, quantum stochastic resonance, the thermodynamic clocks, and which was a very interesting talk given by Gerard Milburn, looking at the properties of clocks and the implications for our understanding of time. The most recent seminar was a fascinating talk given by Professor Carl Bender from Washington University in St. Louis, Missouri. Carl spoke about PT symmetric quantum theory, specifically the use of PT symmetry properties of a quantum system to remove the a priori requirement that Hamiltonians in quantum mechanics need to be restricted to emission of self-adjoint operators. It was a really interesting talk, and it was followed by a very informative question and answer session. If you missed that talk or any of the other talks, and you'd like to watch them again, they are available to watch on the AIP YouTube channel. Today's speaker is Professor Sougato Bose from University College London, who is going to talk to us about a really fascinating idea, namely the investigation of the quantum properties that may be associated with gravitation. As we are all aware, there are a number of approaches to the construction of quantum theory of gravity, such as loop quantum gravity, string theory, perturbative approaches to general theory of relativity, and so forth. But I think the problem has been the lack of experimental evidence that gravitation has intrinsic quantum properties. And that's why experiments of the type that Sougato is going to be talking today are absolutely essential for us to be able to make progress in this area. Of course, there have been experiments in the past, such as the famous Neutron Interferometer experiment carried out back in the mid-1970s, I think it would have been, by Colella, Overhazer, and Werner, for example, which demonstrated that in their particular case, the Schrödinger equation with a gravitational potential term gave good results when compared to experimental data. But of course, that experiment, in that experiment, the gravitational field is treated purely classically. Even though the interference that results is, of course, a quantum mechanical effect. And it might be that gravitation is strictly a classical effect or a semi-classical effect in some way, or it might be that the quantum nature of gravitation is too small to be measured even in principle. It might be constrained, for example, by some sort of Planck scale limitation that we are not familiar with. We just don't know. So these are fascinating subjects that need to be addressed. And here to talk about these issues is Professor Bose. And with his talk entitled The Quantum Nature of Gravitation, or Gravity in the Lab, Assumptions, Implementation, and Applications on the Way. Over to you, please, Sougato.
Okay, thank you, David. Thanks for also quite an extensive introduction to the area, right? Right. So I think from the nature of this seminar, I don't really know who are participating, but thanks for coming. At least I saw one very good friend and old associate, my first student at UCL a long time ago. But perhaps many others are there. So I say hello to all friends and colleagues and people who are there in the audience. Okay, and thanks to Archie for arranging this invitation. Okay, okay. So I'm going to speak about the whatever is there in this picture in the front slide. Okay, and this is the experiment I'm going to go towards. Okay, but before that, I'm going to motivate the topic by spelling out what are the assumptions which lead to conclude one from this experiment, the quantum nature of gravity. Okay, and it's roughly going to be based on the papers that we have published. Okay, a lot has been done with Ryan Marshman, who is also now back in Australia in the group of Tim Ralph in UQ. So now right. So I will start by giving first a brief motivation. So what is it that we are trying to achieve from the experiment? We are trying to show the hitherto hidden quantum nature of the Newtonian interaction. Okay, so we are familiar with the Newtonian interaction for more than 400 years. But what we want to show is that it is actually quantum. Okay, and what do we mean by the neutron interaction here is not exactly Newtonian interaction a la Newton, but essentially the causal version of it. So the version coming from general relativity. Okay, so the retarded, I can say that retarded, the causal Newtonian interaction. That's what we are going to. That's what we are able to show is quantum in nature if the kind of experiment I've done succeeds. Okay, so of course, to show something is quantum, we first have to explain what it means for an entity to be classical, right? So we first describe what is classical, and then we say the assumptions, okay, under which entanglement is not produced if we assume an entity to be classical. Okay, then I will proceed, present our schematic protocol, okay, which you saw on the title page. Okay, and this actually combines ideas from quantum information, okay, into the field of levitated nano objects. Okay, now a little bit of history, if I have time, I'll give, and why other ideas previously proposed are just stopping short of what we are saying here. Okay, then of course there's the important topic of experimental challenges. Okay, what are preventing us doing it? Okay, at the moment, and what has to be overcome. Okay, they're not insurmountable, but they're very hard. Okay, and why taking this line would in general be a very fruitful endeavor. So it will lead to really extreme sensors for classical gravity also. Okay, so for example, David mentioned this COW experiment, COW experiment, very famous 1975 experiment of Colella, Oberhauser, and Werner. If we succeed to make the kind of interferometers which are a stepping stone for our experiment, okay, then those will also be extremely good sensors. Okay, even sensors for gravitation, low frequency gravitational waves. Yeah. So, of course, an important open question is whether gravity is quantum. Okay, we are not really here looking to find out the particular theory of quantum gravity. Okay, so we are not putting so much ambition here. We are trying to just ask a question whether or not. So it's like a yes/no question. Okay. Now, of course, one could try to use old quantum mechanics for that. Okay, what is old quantum? What I mean by old quantum mechanics is energy level quantization. Okay, things like gravitons come in small packets of energy, h bar omega, and with h cross k momenta. Okay, if you are wanting to detect it either from, energy quantization or a momentum kick to your apparatus, okay, this is a very, very extremely, hard endeavor, okay. You have to detect like a nanokelvin change in temperature, okay, or even for relatively high frequency, those detected by LIGO, okay, those kind of waves, okay, in your whole apparatus. And not only that, you have to detect it to the level that you match it with h bar omega, okay. So when you're trying to match something numerical, something quantitative, it is very hard, because qualitative matching is far easier, okay? Maybe it'll become more clearer what I mean by qualitative matching, okay? So it is an approach people can take, and indeed there are very interesting papers recently. It depends on what kind of sources you have in the universe, okay, and maybe there is very tough, okay, to the energy level quantization, okay. Now there is also possible. So what has been done in electromagnetism historically is to detect corrections beyond the Coulomb potential, for example, okay, or corrections to various magnetic moments and stuff, and very historical stuff, okay. Unfortunately for gravity, all these turn out to be extremely small, okay? Even for kinds of distance that you can come, okay. You cannot come too close because electromagnetic forces take over, okay? So the question is that we are living in and not only electromagnetic, maybe other forces take over. So yeah, we better not come very close, okay. And then if we don't come very close, then to have rightly the Newtonian force as we know it, then can we detect whether it's quantum? And the answer is yes, because we are trying to use ideas coming from quantum information, which is after, for example, I would say that is new quantum technologies, okay, or new post-quantum information, quantum mechanics, okay, is we will namely use this following thing: entanglement conveying ability. Okay, if something can convey entanglement from one place to another, okay, so if there's an entity which can convey entanglement between two objects, then that has to be quantum. Okay, so this is the core thing that I will be using. Okay, and also this last point on this page. So we will only show one non-classical aspect of the gravitational field, okay, by this mechanism. We will loosely call any non-classicality as quantum. Okay, when we speak to people from foundations of quantum mechanics, okay, there is the important issue that quantum. What is quantum mechanics? Comes with a lot of things together at the same time, right? It's not just the superposition principle, though that is probably the most core and basic entity there, okay? But there are quantum measurements. So a baggage of things comes together at the same time in the whole Hilbert space structure and the measurement postulate. So we are not, we don't know whether we are proving everything here. We are proving one aspect of the thing which cannot be explained if the entities were classical. Okay, so but that non-classicality is our signature for quantum. Okay, so we are being a bit loose here to call non-classicality as quantum. Okay, okay, right now. As a backdrop, I would like to point out something which definitely was was in the back of my mind, and definitely these kind of things inspired me to think in this direction. Okay, for a long time, one very fruitful way, okay, to do quantum gates, and probably one of the earliest examples is when Serge Haroche collided and entangled two atoms in a cavity. But when the main collision, these two atoms were just passing through empty cavity. And what they did was they emitted and they exchanged a virtual photon. So, and this essentially is the main technique people use these days, or at least one of the most frequent techniques in superconducting qubits. Okay, so what happens is the intermediate bus, okay, is only virtually populated, and it never really entangles with two systems, qubit 1 and qubit 2, but nonetheless is able to entangle them. Okay. Now, why do you connect them with a quantum bus? Okay, because a classical bus does not work here. Okay, so if you continuously decohere the system in the middle, you will not end up entangling qubit 1 and qubit 2. Okay, so you have to start with qubit 1 and qubit 2 to be in a separable pure state. Okay, you know this is in psi 1, this is in psi 2, and then you want to do a quantum gate to entangle, and you would never succeed that if the bus connecting them was classical. Okay, and this is why you need a quantum bus, though this quantum bus is never actually changing its state. If it is 0, the very large approximation is remaining the virtual in the 0 state. Okay, so virtual photons are being achieved. This is the only way to make a coherent interaction between two entities without involving the intermediate one, and it's widely used in implementations of quantum technology from very long ago. Okay, of course we know from more history, okay, even that any interaction is like that. Okay, any electromagnetic interaction between two charges or two dipoles through space is exactly like that. Okay, we just don't see the mediator because there's the vacuum, and the mediation is bound by all the virtual excitation of all the modes in the vacuum, right? So this is essentially the kind of way which forces arise. Okay, and of course Newtonian force can also arise in exactly the same way. Okay, so one can there's a fully relativistic treatment of it, where you can have virtual gravitons being exchanged between two sources, and leads to the Newtonian force if the sources are stationary. Okay. So we are exactly going to ask this question: is gravity like the other forces or not? Okay, that's the main question. Okay, so of course, other forces we know, EM exchanged by photons, then the weak force and the strong force. Okay, all exchanged by due to exchange of virtual quanta. Okay, the question is the gravitational force, the Newtonian force, due to exchange of gravitons, okay, in the same way, or is it qualitatively different? That's the question we are asking. Okay, what we know is that if there's a quantum exchange going on, yeah, if a quantum particle, a virtual particle can, a virtual exchange is a very quantum process, because the particle exchange is in a superposition of all possible energy states. Okay, even which are not satisfying energy conservation, so off shell things. Okay, so it's exactly like the virtual excitations we use in implementations of couplings between qubits. Okay, whether it's a quantum exchange or a classical exchange. So the classical exchange, in a cartoon way, I have shown here as something being continuously observed. Okay, if something is continuously, a classical system is something, a ball rolling. Okay, if you observe it, you have no effect on it. Okay. So the question, the important thing is that if it's a classical entity, then these masses, it cannot convey entanglement. So two masses interacting by a classical exchange cannot entangle. Okay. We are going to make an experiment which will, show you where we'll try to entangle two masses essentially. Okay. So if it cannot entangle, okay, then it then it has to be classical. If it does entangle, it has to be quantum. Okay, because classical cannot entangle. Okay, so now we start by spelling out. So there are some assumptions, of course, on behind our experiment. Let me try to clearly specify them before I go into the experiment. Okay, so of course, one is the most crucial assumption here is that the locality of physics, okay, locality of interactions in that which is we are forced upon it due to relativity, right? So essentially, the locality makes us having to compulsorily to have to use fields, okay, have to use mediators, okay. Otherwise, two masses would interact by action at a distance. Okay, we know when you respect relativistic causality, interactions between systems have to be, local sources interacting with local fields. So H mu nu is the small perturbation on the gravitational field. Okay, we are using this setting because in our setting the gravitational curvature will be very weak, so that we can think of gravity as one would normally think of a quantum field. Okay, so on the flat Minkowski background, it is a tensor field which is present. Okay, so we are working in that strength. Our experiment is in a regime where that kind of strength is there, so we can work with that. Okay, and there our assumption is that the coupling is local. Okay, so what does this mean? This means that you can do only local operations. Okay, if this coupling is there, okay, the operations that you can do between a source and a field are local. Okay, just locality of physical interactions. And then we also have to, as I said, we have to upfront define what I mean by classical, because people could have different definitions of classical. And if you have a rather different definition of classical, then if you expand the definition of classical, then of course you might be able to get entanglement, right? So our definition of classical is the following: that this J, X, and bra here, that represents quantum states of matter. Okay, so it can be any kind of superposition whatsoever. So matter is allowed to be in any kind of quantum superposition. Okay, and corresponding to every state of matter, there is still a classical gravitational field. Okay, so these are denoted here through a curvature. Okay. This is just a cartoon, okay, but there is a classical field created around the whatever is your mass. Okay, it may not be necessarily this field. We are not telling what is the shape of that field. Okay, we are saying that there's a unique field created, okay, which is classical, so defined as numbers or tensors at every point in space-time. Okay, corresponding to any quantum state of the matter. Okay. However, this can also happen with different probabilities. So we are allowing for what I call a statistical theory. Okay, so we are allowing for a classical statistical theory. Okay, you all know what is a classical statistical theory, classical probabilistic theory. So you have different classical things but happening with different probabilities. So that is completely allowed. So fluctuations are allowed. Sometimes people confuse fluctuations with quantum. Okay, fluctuations are not quantum. Fluctuations are very classical. Yeah, quantum is when there are fluctuations in more than one variable. Okay, so unless you have shown some entity you have shown, if you are trying to show quantum from fluctuations alone, then a classical statistical ensemble does not suffice. Okay, as we know, quantum mechanics is characterized by fluctuations in complementary variables here, not commutation. Not a non-commutation in complementary variables. So quantum means if you were to take that route, this is not a route we are taking, okay? But if you were to take that route, you have to show that there are fluctuations in two non-commuting variables. Then it is quantum. Okay. Otherwise, we can just have just give classical noise, and that is not quantum. Okay. So our classical field is defined taking into account that it may be fluctuating. Okay. Okay, so now the central thing which we will use, okay, so this is coming from quantum information, but it is a very simple thing to see, okay. So if you are allowed only local operations and classical communication, okay, so local operations is when you have a matter coupling to a local field, okay, that is so as I said, that can only allow you local operations. Okay, local operations can also be a bit more general. Okay, so that's why I've kept these measurements and things also into account. Okay, you can interact with some other field or other matter locally and then don't observe it, like trace it out. Yeah, so all those things are possible, but those are all local operations. So those are the most general thing possible. Okay, to interact with some other things, observe them instead. Okay, that is a possibility, or you just do unitary operations locally. Okay, and the other thing, which I said in the previous slide, I said that no matter what the state of the matter is, that sources a classical field, means that sources only numbers at different points in space-time. Okay, so if you know, think of a given time slice, think of a given time, then the mass at the other end, yes, this Alice's system, okay, is just seeing a classical field. Okay, so that means what it has received from Bob is a classical number, okay, or a collection of classical numbers in various points in space-time. Okay, the classical number may be different here and there, okay, as was in the COW experiment, for example. So can receive different classical numbers in different points in space-time. Okay, those classical numbers, okay, can to arbitrary precision be thought of, you know, a sequence of bits, okay, in some sense. So it's a classical communication. So when I'm speaking with you, from London to Australia, of course I'm sending lots of classical bits, okay? But that does not allow me to entangle a system I hold, or a system in some lab in Australia. I would really need to, you know, have a satellite and send photons, and, you know, like people do quantum cryptography, you have to send photons and entangle. Okay. What, of course, I don't want people to confuse with is that the mechanism by which an interaction takes place is virtual particles being exchanged, not real particles. Okay. However, just coming back to the thing that local operations, if we assume for simplicity, if we just took unitary operations and you take two states initially, just psi and phi, you can see they will just evolve phi dash and psi dash products. It's very easy to see. Yeah. And similarly, if you took what we call more generally a separable state in quantum mechanics, okay, rho IA cross rho IB, then also you can see that if you used coordinated actions, okay, on these two systems, okay, you cannot entangle them. Okay? So it's just a combination, a more glorious combination of these things with additional systems and tracing them, measuring them. Okay, so it's the same thing. So under this situation that you have locality of physics denoted by relativity. So relativity is an assumption here. Okay, that if nature is local by virtue of relativity. Okay, and if we assume that we can only communicate classically, then you cannot entangle two systems. So now now I come to our experiment. Okay, so what we consider is the following scenario. So we have created a spatial superposition of a mass 1 and a mass 2 in adjacent interferometers. Okay, and now for the moment consider the situation. Of course, is a very dynamic experiment. Okay, it split and it recombined. Okay, but I would, for simplicity, we would describe it in the following way. Okay, so we create superposition of left and right, L plus R in the left interferometer, in one interferometer, and left perspective the other interferometer, and we consider the situation when they're held next to each other for a while. Okay. Okay. Say the centers are separated by D and the superposition size is delta X. Okay, so the circled and the dotted versions are superposed. Okay. So how the evolution happens? So we know it just with different frequencies, these different components will evolve if they are interacting. So let's assume they're interacting only through gravity at the moment. Okay. Later on, we will show how to get rid of other forces. Okay. So if they're interacting only through gravity, then this is just the Newton's gravitational potential. Then E by potential energy between the two masses, so E by h bar times tau. Okay, that's the phase for each component. Okay, so equal to h nu. Okay, so the different phases evolve at different rates. Okay, and we will consider so now what happens to the mass under this situation. So let us see a special case. So we can take out a common part of the phase, which is left, left, and right, right. Okay. If we do that, then you see this L, okay, is partnered with L plus e to the power I delta phi L, and this R is partnered with something else. Okay. So this is not a state which you can factorize out. You cannot take L or R common from here, or even this part common from here. Okay, so this is an entangled state. Okay, when it is even what we call a maximally entangled state, when this kind of condition is satisfied, because then the second part is orthogonal to each other. So it is such a highly entangled state. Now the question is, so if we can achieve this kind of phases. Okay, so we will try to achieve a phase. Okay, we'll try to see what is needed to achieve this phase for this maximum entanglement. Now, it is very important to consider a limit in order to see the maximum possible strength of the effect. Okay, the effect in practice will be weaker. Okay, because experimental issues. But suppose you consider a situation that we bring the right and left so close to each other. Okay, that right and left are extremely close compared to the superposition sides. Okay, so L and R are separated by distances delta x, which are far bigger than how close R and L have approached. Okay, so in that kind of situation, we can consider only one phase. Okay, the delta phi RL phase. Okay. Now, okay, so one important point regarding how close you can bring them. Because we don't want them to interact electromagnetically. Now you see, my colleagues have extremely good techniques, which I knew about when we were writing this paper, is you can neutralize masses to extremely good accuracy, okay? Trap masses, you just shine UV lights and things like that, okay, to the masses or to the enclosure, okay? So they can be neutralized to extremely good accuracy. And there may be multiples inside, but those you can take an extremely good single crystal sample, or you can try to physically spin them, okay, so that those multiples are there. But a force you will not get rid of, unfortunately enough, even for completely neutral masses, dielectric masses, is this Casimir interaction. Now, luckily, the strength of Casimir by strength of gravity is something you cannot do much about. Yeah, so it comes out to be something like that for a given distance separation. Okay, this is the mass Planck square, so obviously you cannot do something about it. Okay, you cannot do too much about the density, okay, of objects. Okay, you have typical solids. You may go to extremely dense solids if you want, but you know there's a limit. Okay, so essentially for types of objects which people are levitating and doing experiments with. And there's not too much freedom beyond that, okay, is to have at least 200 micron separations. Okay, this might come as a surprise to some people. Yeah, indeed, often experimentalists say, okay, so 100 nanometers, 1 micron, maybe you do not have that much Casimir. No, it's for the kinds of mass, for any mass, okay, for gravity, because it's so big, to dominate over the Casimir, you need 200 micron separation. Okay, so this is bad news for us. Okay, so this means this closest approach, R and L I was talking about, yeah, has to be at least larger than 200 microns, which means if we want to take this limit, these separations have to be larger than that, or at least comparable in a realistic experiment. So it means creating large superpositions in interference experiment, which is tough. Okay. Now, what is the magnitude of the effect? Okay, so for which we took micron-sized spheres, they have 10 to the power minus 14 kg mass. Okay, and as I say, to prevent the Casimir, we have this 200 micron separation. Okay, now I allowed the luxury of 1 full second, which is an extreme luxury in terms of coherence. Okay, and then we took the superposition size, comparable. Okay, so then we get this phase. Okay, this you hold for 1 second, you will see this phase here, okay, it turns out to be of the order unity. Okay, so this is here the Planck's constant, in the denominator is actually fighting the smallness of the capital G, the Newton's constant. Okay, and that's why we are able to get a kind of unit order phase. Okay, some other people analyzed our experiment and rewrote the thing in a slightly different way, where you can see that our masses within microspheres, they are still many orders lower than the Planck mass, but kind of getting there. And the rest is compensated by, during the time of our experiment, light travels a long distance. Okay, so that way you can think about it, or you can just think that capital G and H bar are kind of both small. Okay, so that's why you can get a unit phase shift in 1 second. So it's a Hertz frequency experiment, okay, that you can entangle two masses, microspheres, at a Hertz frequency. Okay, that itself is very exciting, of course, that you can use gravity to do something at a 1 second time scale. So I will just see that there seems to be a question in the Q&A. Why does the equation with Casimir ratio have D rather than D minus delta X? Okay, so this is just a order of magnitude thing. Okay, so the delta X's are important only when we are doing we are applying it to the superposition. So I'm just estimating. So you're right. Technically, it's D minus delta X. Okay, but so we have to be careful that okay, yeah. So the D, if we mean by as I meant by D, the separation between the centers. Okay, here what has to be 200 microns really is not D, but D minus delta X. You're completely correct. The person has put the question there. Yeah, so the closest approach has to be 200 microns. That's true. Okay, I use D just as a symbol there, a bit loosely. Okay. Now let me go to a little bit of history, okay, before going to how we will physically implement that. Okay, so earliest example of this kind of thing was given by Feynman. Okay, that you took a mass, okay, created in a superposition of up and down, okay, and you could make it move both ways, okay, using a Stern-Gerlach-like experiment. And indeed, we use this pretty much the same thing. Okay, we did not read Feynman's Chapel Hill proceedings, of course, when we were talking about this kind of thing, but essentially this is a very good way of creating superpositions. And so, and then if you have another mass, Feynman suggested it will move up or down, okay, according to this first mass. And then he said that to describe this kind of experiment, you have to use amplitudes, okay, and that would you would need to. So these exact words are quoted here, that you have to believe in gravitational quantization in order to describe this experiment. By describing this experiment, he probably meant all aspects of this experiment, but it's not clear. It's just words there. Okay. So what we have realized is the aspect that you need to check here is the entanglement between the two systems. Okay. So we are essentially looking at a two-particle interferometer. So the question is why. So that is one of the things. So this is the way we are kind of becoming more concrete than what Feynman had alluded to. Okay, a long time ago. Okay, more than 50 years ago. And then there is this question of do we really fully need to entangle? There have been suggestions from time to time about detecting the deflection, just the deflection of a second mass based on the first mass. Okay, so the motivation was that people were trying to detect whether, when you create a superposition, the gravitational field sourced by it, whether it is centered at the left or centered at the right. Okay, and then you could try to see it from the deflection of a second mass. Okay? There are many proposals in this direction. However, why they are falling short of entanglement is the fact that this is testing the statistical character of such a superposition. Like if the mass is centering a gravitational field in the left, half the time with probability PL and half the time with probability PR, in another place. So it's testing a classical statistical character, but not really a quantum. Quantum is about the coherence between those two centered fields, okay? And to detect that coherence, I do not think anything shorter than testing the entanglement with another mass can suffice, okay? Or some experiment which is of the similar order of strength and time and coherence requirements, okay? So and also people have started using different masses and things. Since the M square effect, you're having to create both in superpositions, it makes sense to use the similar kinds of masses. Now, how will we create this kind of superposition, which is large mass, large splitting, okay, and long duration? Okay, this is what I call these kind of superpositions. And how will you detect that entanglement? So first of all, we cannot use the simplest trick people use. Yeah. So to create superpositions in the micro world, we just use a beam splitter. Okay. Indeed, people have done such things with BECs and stuff. Okay. That is this kind of dichotomic superposition is ideal under beam splitter. This is not possible here. Okay? Simply because of this fact. Okay. That if you have a beam splitter is a tunnel barrier. Okay. And you have to create a superposition, so you have to split over some distance, okay? And if the masses are large, this height becomes abnormally small, and then of course the thermal effects are strong, and that doesn't make sense then to have this, left and right. Okay? So it is extremely difficult to make a beam splitter for a large mass of the size I'm talking about. Okay. There's a question here also. Oh no, this is the question I answered. Okay. Now, so what we suggested is to use an internal variable like a spin. Okay, so you create initially a spin in an up plus down state. Okay, and then you subject it to an inhomogeneous magnetic field. Okay, so this is the submagnet south and north. Okay, first inhomogeneous magnetic field. The spin splits. The up component, accelerates this way, the down component accelerates, just a Stern-Gerlach effect, they accelerate oppositely. Then at a certain time, quarter of the time of the experiment, the spins are flipped, okay, so that the components start decelerating, okay, they stop, they turn back, then they again speed up, okay, and 3/4 of the time they are again flipped, okay, so they have been speeding up, so now they decelerate and then they come together, okay. So it's both the wave packets, they have to be brought to completely overlap with each other, not just in space, but also in their momenta, which is why we have to use this special protocol, which also, slows them down to exactly overlap with momenta. Both momenta become centered at 0 and both position become centered at 0. So this is the time axis. So it's a 1D interferometer. Okay. This kind of thing is called Stern-Gerlach interferometry, has been already widely implemented by Ron Follman. Okay, in atomic experiments, and indeed we also recently collaborated in a paper with him, but he has been doing it for a while. Okay, we did not again know that when we proposed this for macroscopic objects, but we have proposed that in 2013, 2016, and this is a way to achieve large superpositions. Now we bring two such apparatus next to each other. Okay. The question is what happens to the spins embedded in the masses. You see, so we have a spin initially in a state up, okay, up plus down, when you have this interferometer. When they close, if there was no interaction, both would come up plus down in a separable state. But if you follow the maths that I did before of entangling the masses, only now you replace every left with left up component having gone left, and every right component with down. So just replace symbolically L and R with L up and R down. Just repeat the maths, and at the end of it, to your wonderful surprise, you will find that the well, not surprise really, it's obvious in retrospect, but if you will to your wonderful delight, you will find that at the end the two spins are entangled. Okay, so the masses, the center of masses of the objects you see have been brought back to overlap. So they are not now correlated at all. Okay, they are both center 1 and center 2. Okay, like this. Okay, but the spins that have been embedded in them, which were enabling creation and recombination of the superposition through the Stargard array, those spins end up being entangled. Okay? And this can be measured. You must have heard of Bell inequalities. Through spin correlation measurements, you can measure entanglement. Okay, there's a certain kind of correlation you can measure, which we call an entanglement witness. Okay, which for this particular state will reveal its entanglement. So you have to measure these kinds of spin correlations, a spin of one and spin of another. Okay, so those spin correlations can certify the entanglement. And if we do get entanglement, we have to conclude that the masses were quantum in nature. Okay. So I would like to know how much time I have now at the moment. So otherwise I have to, so just to speed up a bit. So if maybe, I mean, how much time do I have left?
Oh, I don't think you should worry too much.
Okay.
Yeah.
Right. So maybe I speak for another 5 to 7 minutes.
Oh, yeah. Certainly. There isn't any.
Okay.
Yeah.
Okay.
We're only worried about your time.
Okay. No, that's great. Okay. So of course, one very important thing here is to this Casimir force was a troubling thing, yeah, for which we had to go to these 200 microns. Okay, but these 200 microns place the limitation, as was there is related to the question you asked to me. Okay, so when you make these 200 microns, then you have to make this delta x also, like 200 microns. I mean, we made it 100 microns to get a like smaller value of the weakness. Yeah, not terribly small. I think point something, so 10 to the power minus 1 order. Okay, but the mass was also 10 to the power minus 14 kg. So, but if you put a screen, a conducting screen in the middle, okay, then you can screen the Casimir force at the expense of developing new forces between the masses and the screen. There will be a Casimir force between the masses and the screen. So you can take all that into account, and then if you also sacrifice the phase a little bit, okay, that means essentially also sacrificing the weakness by the same order. So when phases are small, weakness is of the same order as the phase. Okay. So then we can get to one lower order of mass, 10 to the power minus 15 kg, as well as one lower order of superposition, 10 microns, okay, and also requiring reasonably small magnetic field gradients. Okay. Now, so when you so now there are lots of noises. So what are the noises which are affecting us? Okay, so there are two types of noise. Okay, first of all, there is a noise due to random accelerations received by the mass due to external objects. Okay, because they like the famous COW experiment that David mentioned. What happens is they will give random phase shifts to the apparatus. So they will, scramble our phase, the phase we want for giving the entangle, make the entanglement less because they are inputting noise in that. Okay, so that is something we have to think about. Okay, the other thing we have to think about is random momentum kicks and things from on an individual interferometer. Okay, from things like in this case, the two most important things are the masses are surrounded by a vacuum. And that vacuum is not, I mean, there's not really true vacuum, so there are atoms there. Yeah? And so that depends on the pressure, okay, and the radius square of the mass, as you may, I mean, that's the area presented to these impinging atoms. So that goes as R square P with lots of prefactors, okay, which I have not written. It compels us to do at low pressures of 10 to the power minus 16 pascals. Okay. This sounds extraordinary to most experimentalists, okay, but believe me, in penning traps, in Harvard in the early 90s, they have done so. Jerry Gabriel's group has done lower pressures. Okay, they can't measure the pressure at that level. There's no gauge. Okay, so in principle possible, but you have to have tremendous effort. Okay, to enclose our experiments in that kind of pressure. The other thing is that black body radiation also reveals things. Okay, and essentially the point is that so both for atoms and black body radiation, this holds that they essentially carry which way information. That's why they decohere. Okay, if an atom was to hit one component of the superposition and scatter, okay, since its de Broglie wavelength is so typically very small, okay, at temperatures we can think about, okay, it will reveal whether it's in the left or the right. Okay, that information will be there in the environment. Okay, so it decoheres. Okay? That's why we have to reduce the number of atoms, okay, in the environment. And the black body radiation does a little bit of different. It at the temperatures, the wavelength emitted is larger than our superposition size. So it doesn't immediately reveal left or right, but after a lot of hits, it will gradually, tell you the position. Okay, so that depends on the temperature of the object. So internally, the nano object has to be cooled to 150 millikelvins. Okay, this is tough. Yeah, we know 4K is easy, right? Helium. Okay? But this is tough internally. So we have to think about these things, equilibrating with in a magnetic trap, in a dilution fridge or something like that, and then proceed from there. Okay. Now, the other thing I was mentioning is this random acceleration noise. Okay, so there, when you have these masses and you have create superposition, you see that extremely tiny acceleration, therefore -4 meters per second square or -14 meters per second square in very short times, okay, can produce significant effects. Okay, and they will dephase, they cause unit order effect. Okay. So what do we do for this? Okay, so we fight gravity with the principle of gravity. Okay? So in some sense, this is Newtonian noise. Okay, so we fight Newton with Einstein. Okay, in the sense that we use the equivalence principle. So gravity can be made to vanish, okay, when you are in a freely falling frame, as you know. So our lab has to, if we, this is one way to do. I'm not suggesting this is the only way to do. We would really like to find out better ways of doing it when we create such large superpositions. Okay, but for the moment, this is one prescription we have, is to place both these apparatus interacting with each other in a freely falling lift in a drop tower or something like that. Okay, so then what happens is noise due to all external randomly fluctuating masses would vanish because the whole lab would, shift accordingly. Okay, accelerate accordingly. Okay. However, something is still left, which is because these superpositions are themselves a bit spread out and they are also separated. So it is the curvature of this, this external mass produced here that matters. That can also create a noise. Okay. So the first kind of noise in this freely falling situation, of course, though, is that the vacuum under which it freely falls is not that necessarily good a vacuum. So there are some random accelerations due to that vacuum. So we have found conditions where a reasonable capsule, okay, of so this is the usual ZAM capsule, but you see you have like a between 1 to 10 kg capsule. If you can get 10 to the power minus 10 pascals of pressure. Okay, so that's possible. Okay, so standard UHV, okay, can in principle do this experiment in a drop tower, and the noise due to the curvature of external masses, as you can see, it requires an exclusion zone. Okay, so if external masses are far enough, then the curvature they produce is small, right? And curvature is quite can be rewritten in terms of the acceleration they produce. Okay, and the acceleration noise has been widely studied in LIGO. So a lot of data was there from that. Okay, so we could use that those noise spectra, and we found that essentially these are the exclusion zones. Okay, so what is the smallest exclusion zone is this dark green line, which is human smooth motion. Okay, we have to be 5 meters away. Okay, other things have to be further away. Now, last but not the least, that I want to like to emphasize is that if we take effort to build such a such an interferometers to entangle them, okay, we and in the end, if you think back, our answer is just we are going to be able to say whether gravity is quantum. So this is just like a one bit of information. Okay, if the experiment fails, we cannot immediately conclude gravity is classical unless we have enough to make 100% sure there is no decoherent sources. Okay. Or that gravity acts in a very different way. Okay, so we have to we have to think a lot if we get a negative result. But if you get a positive result, you can immediately conclude, however small the entanglement, if you get you can conclude because entanglement has to happen systematically. It cannot happen spuriously. Okay, there has to be a systematic course in every run. Okay, so that we can so in principle we can hope for a one bit of answer whether gravity is quantum. Okay, and should we devote a lot of money and energy to that? That's the question. Okay, it will be a new knowledge. Okay, but we won't have the quantitative theory of quantum gravity. I mean, we cannot say, string theory is correct or loop quantum gravity is correct. We cannot do that. Okay, we cannot tell anything about Planck scale physics. It's just an infrared qualitative character, whether it's a quantum field. Okay, now so we might as well have other applications, and this is the good thing about it. If you create if you can create such interferometers, so here you can see an asymmetric superposition. Okay, so essentially you need to superpose variances. Okay, so we have one path with a large variance, one path with a small variance. Okay, it's possible with two components of a spin, one object, for example. Okay, there may be other ideas. Okay, then you can see that so this is the whole phase of each of these paths written down. And as you can see, we are trying to detect, we are saying that can we detect these gravitational field components, Hij? Okay, so you see they are strongly suppressed by the velocities that we can achieve, which are indeed very small compared to light speed. Okay, we can take that common. Okay, on the other hand, we are compensating by the mass. Okay, if you take, say, for example, take atoms to detect, it would be exactly the same phase, except that the atoms would be much smaller. Okay, so the mass being much larger helps us make these velocities much smaller than you would require to do it with atoms. So essentially helps us to make this interferometer compact. Okay, you can do the same thing with atom interferometry, but you will need thousands of kilometers, even in 10,000s or 100,000 kilometer long apparatuses. But because our masses have gone up so much, it's a product in the action of mass times the distance here. In this case, the velocity, it will be distance squared. Okay, we can rewrite it in an appropriate way. So we can make compact apparatuses which are meter scale and keep for 1 second and take a slightly lower mass than what we had for testing the quantum nature of gravity. That needed a larger mass because you're sourcing gravity to be in a quantum state, okay, from the superposition. But here you can do with smaller masses because you're just making one apparatus and detect it. Okay, so it's just like the cow experiment, except that we are showing that when you use these nanocrystals, you can detect classical gravitational fields. Okay, classical gravitational waves. Okay. So then here is the thing that this is good for this spot where you have less than 1 hertz, so like 0.1 hertz, 0.01 hertz kind of fields. Okay, this is because we take some time to create the superposition and back. Okay, if the field is much more higher frequency than that, then the effect cancels away. Okay, so we kind of need we can do anything in the lower side, but if you were to do on Earth, then so we calculated other noises will come in here, the seismic and atmospheric noise. So that if you do in space, you can continue this dotted line. And this is what happens with atoms. And this is just a rehash of the what we are saying here. So we are kind of detecting this kind of superposition, that the source and the two sources of the gravity are placed differently. So the virtual excitations of the gravitational field must have been in a quantum superposition during our experiment. Yeah, so I think I would like to conclude. I can clarify further during the questions. Okay, so this is the papers we have written in the topic. So the main paper. So these are some of the background things. Then this is the main paper I spoke about. As you can see, Gerard was a collaborator in that paper, right? And so there's a lot of Australian contribution to the work there, because also my later work, Ryan Marshman has been a collaborator who is now back in Australia. And these are the things we have done. We have also recently looked at other things such as Q dates and participated in an actual experiment with atoms, which is not really, going to the level of nanomasses, but Ron Fallman definitely wants to go there. Okay. Yeah, so I would like to, I would I'm happy to take questions now. Thank you for your attention.
Thank you very much, Sougato. That was a fascinating talk. Just while people are formulating their questions, so you may have covered this. So it's probably, this is a thought experiment, so it's a bit early to start talking about in depth the experimental difficulties of doing it. But if you can just give us a feeling. We were talking about meter scale experiments in one context, and we were talking about perhaps smaller scale experiments in the other context. Would it be true to say that, I mean, one of the things that's fascinating about this is the fact that we're seriously proposing to be able to directly detect the gravitational interaction between, particles which are nanoparticles, which are very small. And this is totally counterintuitive, Would it be true to say that one of the reasons that it's possible is because the relationship between the nanoparticle mass and the Planck mass? Is that true?
Yes, correct. Yeah, so that is one way of checking that. So when we said so we were coming from quantum information, quantum optics background, most of us, the co-authors of the paper. So we did not write it in terms of Planck mass. So we were just thinking that, of course, capital G is small, okay, but we have come sufficiently large in M, and then H bar is so small, so quantum phase still can be very, if you look at phase evolution, okay, then it can always be amplified. We were thinking that way, but you're right. Perhaps another good way to put it is that essentially it is M square by MT square effect, right? So we are now gone to a substantial fraction of the Planck mass. Okay, we are still 10 to the power minus 14 kgs, so we are quite a few orders, like 3-4 orders lower than the Planck mass there. But that is more than compensated because you also have a light speed and time. Okay, so this spot is enough for us. Since then, what we have done is we have tried to go down in mass. Okay, so you can go down in mass to get a smaller phase and proportionally smaller witness value.
Yeah.
Okay, so but that means that the number of experimental runs will go up because it's just one. So number of experimental runs, if it is n, then 1 by square root of n is the precision to which you can detect the witness.
Yes.
Just short noise thing. So it's so in the end, one has to choose an appropriate regime of what is easier. So slightly smaller masses, more experiments, or larger masses, less experiments.
And if the experiment is larger, you've got an opportunity to acquire a larger phase shift over the baseline length of the interferometer effectively. Is that right?
Yeah. So larger masses would mean that you have, so the regime which we propose in the experiment, you essentially, it is entangling fully. So it's like an order of 1 run. Okay. Since you have to evaluate a correlation function, it will not be 1 run exactly, but it will be order of 1. You see? Right. So that's the thing. So maybe 100 runs or something like that would be enough to completely determine. That's the regime so the regime is probably too strict in this spin entanglement witness paper. And since then we have been trying to loosen up and loosen the constraints. So we have achieved to go 1 order lower in both mass and distance with this extra screening. But we would like to go more, okay? Yeah. Recently, other things have been thrown up that this creation of the superposition itself, the scheme we proposed, also recently appears to have some limitations. We have to overcome these things due to the diamagnetic nature of the objects.
Bruce Yabsley has a question. He said, there was a plot with something like mass of box, size of box, and various different cases shown as curves. It was quite detailed. Could you explain this?
Okay. Yeah, I will go there. Yeah. Right. Yeah. So this is the box in which we are housing our experiments. So both the interferometers. Okay. And then we are assuming this is freely falling in a drop tower. Okay. This is to cancel all, inertial noise from outside. Okay. So if any external mass moves, that simply vanishes because the whole box will accelerate. Okay, the freely falling box, and everything comes. So all final lasers which are measuring the spins are embedded in that. And what we found, but problem is that in that tower where it falls, okay, say or underground tunnel or whatever where it falls, okay, there will be outside will not be exact vacuum, okay. So that those atoms will be kicking the thing, and that they give. So it is known from LISA literature that due to their pressure and temperature, they will give an effective damping, and that kind of gives a decoherence between these. So it gives random phase shifts again, okay, of each interferometer, which will decohere. So that's why we have to make these things. So you can still have room temperature for the whole drop tower. There's an enormous facility to demand to have to cool to low temperature, and the pressures are UHV. So under that, we found that this works. So there are these points are valid. For example, this gray region is the valid. There's gray regions are valid regions. And these are some points where we can construct our capsule.
Okay. I mean, I think you kind of answered a question I was going to ask you when you showed the slide with the potential shield between the two branches that you want to gravitationally interact. Because one of the questions that I was going to ask was, I mean, in these Stern-Gerlach apparatuses, the two channels that the particles go into can be quite smeared out in relation to the distances between the things. So that there's some uncertainties in the sort of lateral momenta of the particles and so forth. And so I was concerned about, I mean, one of the things you have to be sure of is that there's no other entanglement processes going on between other than the gravitational interaction. And one of the things I was worried about was, you know, there would be a non-zero probability for particles in the left side branch to end up in the right side branch and vice versa, so that your detectors would effectively be measuring particles which were entangled by virtue of the fact that you don't know which source they came from. Presumably that's an effect that your shield would be necessary to make sure wasn't a major course of error in this experiment.
Right. So essentially there are two things there that you have asked. So let me first answer the latter thing. Okay. So which is this spreading. Okay. So one of the effects, of course, when any mass is freely falling, because it's not trapped at all, that its wave function is spread. Okay. Now, this wave function spreading, of course, depends inversely on the mass. Okay. So that is here to our advantage, that the wave functions do not spread too much beyond where they have started, okay, due to the natural, p square by 2m dynamics, okay. And in fact, what you have to, what is satisfied automatically is that the left-right separation that we are demanding, since it is so much, right, to 100 microns, okay, these 10 to the power minus 14 kg masses, or even 10 to the power minus 17 kg masses, do not, in 1 second, okay, they will not spread so much. Of course, that little bit depends also when you're starting with, starting them with a trap. Of course, you cannot, if you started with a delta function, they will spread. But we start with, a ground state in a cooled trap. Okay, where, because again, for the large mass that is small but has some spread, so then you can use the standard wave function spreading formula, and that spread does not happen. The L going to R is just because we have solar. Now, considering other forces, okay, the things we have looked at are, so as I said once during the talk, so if something is to entangle, so how do we verify entanglement? By doing many runs and, by observing correlations. So all those have to be producing the same state, okay? If one produces one state, other produces another state, entanglement will only go down, okay? So what we are looking at here are systematic forces which are happening from run to run, where every run, is the same. Like gravity is the same in every run as part of our, preparation. Okay. Now, so of course, the main things you would think about first is the most troubling thing is that if the mass has aqueous charges, okay, this can be extremely well, controlled by UVs on the environment or on the UVs on the environment or on the on the closure, okay, according to positive or negative. So then they cancel those charges, and this has been done exquisitely well. So you can really have neutral nano objects. Okay, what is much more difficult is that there could be charge multipoles inside, starting from dipoles. Okay, so that dipole-dipole interaction is going to be again much stronger, okay, than gravity. So this is why one of our co-authors was suggesting that you physically also spin. Okay, this we have not yet explored in a great detail. So if you put a physical rotation, then those multipoles will average. Okay, only one direction they will not average, but that's not the gravitational interaction is perpendicular to that. Okay, so having got rid of those two electromagnetic interactions, then you have what is called the Casimir is the only thing left. Okay, and then you the direct. Some people ask me of the direct spin-spin interaction, the magnetic dipole interaction, because gravity is so weak. One might think that. So that actually is also much weaker because it's the single Bohr magneton, and the thing is the mass is large. You see, so when the mass goes to below 10 to the power 19 kgs or so, then the magnetic interaction becomes comparable. Okay, so it is just that it is so much larger than and mind you, when gravities become larger, we are operating at appropriate distance, that those are less. And gravity itself is just unit phase. So this is why and then we are operating at such a distance that we will think, that gravity is well studied in those distances much larger masses. So one would not think there are any forces or things at that level of distance.
Right. Interesting. There's a question from Alan Ernest who wants to know, you mentioned at the start of the talk that to demonstrate gravitational quantum effects using gravitationally quantized energy states in the lab is very tough, hence your entanglement approach. Have you heard of the demonstration of the existence of distinct gravitational energy eigenstate of the Earth's gravitational field in 2002? Quantum states of neutrons in the Earth's gravitational field, and it gives a reference to a Nature paper, or more recently, resonant induced transitions between gravitational eigenstates have been observed, a kind of line spectrum for gravity. So there's a number of papers that Alan mentions there as well.
No, that's good. Thanks for these references. So I kind of heard about this topic, but never really try to read this up. But of course, this is more like when I say difficult to see quantization, I did not mean the difficulty of seeing quantization of a mass in a gravitation, a potential which is created by gravity. Okay, so those experiments are extremely interesting. They are taking kind of a next step after Colella, Overhauser, Werner kind of experiment. Rather than just showing the interference, they are also showing quantization of a mass in a gravitational potential. Okay? And so like a gravitational atom in some sense, right? But as you know, an atom requires quantization of the electrons and the nucleus, okay? And a lot of things can be explained with that, not going into the quantization of the EM field. Of course, quantization EM field has effects, lamp shapes and things, but that is a very higher order effect. But so what I was referring to is seeing the quantization of the gravitational field. So the graviton, for example, is very difficult to detect from the energy or the momentum that it puts in, right? There is a recent, quite widely noted paper recently by some other people, right? But again, I haven't yet looked at the details, but the what I say is that it's a very hard task for sure. Just from h bar omega and h bar k, you can see how hard it is. So though our experiment is very hard, and it will not detect, like it's not like detecting a photon as detecting a graviton, okay? So it's detecting a qualitative feature, but it may be still much easier than this other experiment, which is trying to detect the graviton. So I say that in that sense, the energy level quantization is difficult to detect.
Yeah. I mean, one of the things that I was wondering about was whether or not we were worried about other forms of entanglement with respect to the nanoparticles. I mean, I guess effects such as entanglement between gravitons or themselves and the nanoparticles would be too small, right? I mean, we don't really know, but I imagine they would be too small.
We have explored that effect recently. Yeah, it is. It doesn't. It will. This was not in my references, but yeah, we have looked at those things with Anupam Mazumdar and Marco Toros. It's a very weak effect. I mean, other people have also looked at that kind of thing before. It's it is not a hard scale effect.
Yeah.
So we looked at it from the point of view whether it affects our experiment. So of course, if you're wanting to detect it, you could try to see what kind of masses and what kind of times you would require. Okay, but it will be more challenging than the gravitational waves thing we have told.
Which is challenging enough.
Which is a meter scale analyzer. So it will be one more step beyond that.
You just need to get the European Space Agency to put your experiment in orbit or something. That'll solve all of your problems, right?
Yeah, going to space might solve a lot of things, but I don't know. So often often space not necessarily is the most freely for. I mean, it's there are accelerations of the side. So I'm not enough knowledgeable about the topic, obviously. That's the thing. Yeah, I mean, we are kind of a little bit upset that we have to do this in a drop tower itself. Yeah.
Yes.
So there might be alternative techniques by comparing with other sensors. This is something on the cards to look at. But anyway, this is what we are have now. That it is beautiful, of course, because conceptually it is beautiful to do it in doctor, because it also shows the difference. So the entanglement really happens due to curvatures. Okay. So due to true gravity, because it's depends on the difference.
Yeah.
Okay? While all the external things actually give just an acceleration to both. Okay,
yes.
And that you can just cancel. So you can use really gravity's features here. But on the other hand, practically it makes it very challenging. And for space, we have to do similar calculations differently. That's what I would say. And then there are cosmic rays and things. So there are other decoherences.
And if you were to do the experiment, and if you were to get the experiment and get a positive result, so we know that there is some quantumness interacting between these two nanoparticles. How much information can we get about that, other than just a qualitative? How strong are the inferences that we can draw from that, other than to get a qualitative understanding that there is some quantum mechanical machinery sitting within gravitation? I mean, it doesn't necessarily imply, for example, that a full graviton picture is necessarily correct, right? In the sense that Feynman would have envisaged it decades ago, or does it? That's the question.
No, so it is a golden question. What more we can find out? Okay, so I would think that in combination with the fact that it's a coherent interaction up to any time. Again, whether that can exactly be checked in our experiment, I have to think a bit, but the entanglement is continuously growing. The two systems as a whole are remaining in a pure state. Just like a quantum gate is happening between objects. Okay, that would at least enforce the fact that it's only virtual particles which are exchanged. Okay, because the mediator is not getting entangled with the system. Okay, so that much we can conclude, and of course we can conclude the mediator is quantum. But to do anything more than that, we would need to get some kind of quantitative deviation or things. Yeah. So on these aspects, we have not done much yet. I speak with Inertial, for example, from time to time on these kind of things. Okay. Something which Carlo Rovelli and Marios Christodoulou has spoken about is some kind of discreteness of time detection. Okay. But I think well, we haven't seen very carefully what else one can check with it. But this is why we went through the other route. We wanted to check what it can do as a sensor.
Yeah.
So that people have other things to do. But yeah, I think it would be nice to have more to conclude about quantum gravity than just one yes no question.
So Guado, maybe one of the obvious things to look at, what is obvious is to check deviations from GR, say propagating torsion, which interacts with the spin directly, not just the masses. So then you might have some different kind of phase shifts and things like that, and the pattern in your experiment.
No, that's also a very good idea. Essentially, yeah, we can speak about it. I think used to mention torsion in some of the very early days of our discussions, but then it got dropped somehow. But one can check that also. Yeah. So if some, we should have a chat about that definitely. Yeah, among various other things we have planned.
I don't think there are any other questions. Let me just double check, make sure I'm not failing to. I think we've answered all of those questions. So in fact, the answer to your last question probably prompts me to ask, if we get a positive result, how do we, what do you think that says when we attempt to reconcile as much information as we can draw from this experiment to the standard interpretation of gravitation, of gravity in the general theory of relativity, that it's a space-time curvature? Are we going to then draw strong inferences such as the entanglement of the nanoparticles implies, in some sense, the entanglement of regions of space-time? Is that where we're going with this, with these results from a theoretical point of view, or is that drawing too long a bow?
Again, a very good question. Yeah. So again, we have also thought a little bit about that. Again, in collaboration with Ryan, who is now in Australia, and with my collaborator Anupam Mazumdar. So essentially, of course, space-time regions should also be entangled by the same kind of token. Okay? Only this kind of entanglement might be very difficult to find or have a signature about, because it is also entangled with so many other things.
Yes, yeah.
So one has to see what one can do about that. But yes, I mean, yeah, definitely that's correct. Yeah,
so fascinating theoretical direction.
Yeah, entanglement is kind of inevitable. I would say that's the thing here. This force is always there. We cannot be unentangled. So I noticed there was one more question in the, was it
and then there was a follow-up question.
Okay. So
would
there
that
was
imply
something that yeah, space-time isn't fundamental.
Yes, would that
we are I mean, from our experiment, it might be very difficult to conclude. I mean, one can do the same calculation for space-time regions, but it may be very far-fetched to conclude something like that space-time is not fundamental. We are not yet exploring. One can definitely try to see what one can say from these kind of experiments about that, but we cannot. So we are, I mean, upfront I declared we are working as if in this regime where gravity can be treated as a standard quantum field in a Minkowski space-time, rather than as a curvature. Okay, so I'm working in that picture. Makes it easier to work here. That's not necessary. So one can also interpret the experiment as revealing a superposition of curvatures. Okay? And it's just that there's no other way to really conclude a coherent quantum superposition of curvatures, rather than to see the entanglement between two such curvatures. And see, the coherence part demands really the entanglement. So the what we can say about really non-perturbative quantum gravity, I mean, we have not thought much about. I mean, one of the safe thing we are working with in a Minkowski background, so a very standard space-time. The connection, you don't have wormholes and things. So then the LOCC will be in trouble. The local operations classical communication not being able to entangle will make trouble, if you are. Yeah. So Murray says there's a last question in Q&A.
I think that might have been the question we just answered. Is that
okay? I see also something there was something by Peter Drummond that in question answer a long time. Yeah, I think that was a while ago. I guess I didn't notice it. Okay, so yeah, diagonal gravitons, they appears to, yeah, that's so these are all it's true. So we are always working under assumption of there's a good effective field theory of quantum gravity when we are drawing gravitons. Okay, one can, as I said, some other people have argued about our experiments, conclusion in a different way, that it implies superposition of curvatures or superpositions of, different speeds of time running. Okay, so you can interpret it that way. We have just used a very low energy case where it does not really depend on the cutoff. We are assuming that there's a cutoff and it's some UV theory, but the IR theory is standard gravity as we know it, the standard quantum theory.
Well, that's really interesting. I think I'm safe to say there are no more questions. So, oh no, hang on, let me just see. Yes, there is a question from Peter Drummond here.
And it was the one I answered. Yeah, is it?
Oh, that's the one you answered, yeah. He mentions you're drawing Feynman diagrams with gravitons at one point, but there appears to be no proof of perturbative renormalization in quantum gravity. Are you assuming a cutoff?
Yeah. So that's what I essentially told. We are assuming a effective field theory,
right,
to be valid.
Sorry, I almost missed that question, Peter. Yeah. Okay, well, thank you very much, Sougato. That was a fascinating talk. And I'd like to thank everybody for participating in the seminar. It was extremely interesting. If you want to listen to the seminar again, of course, it'll be available within a few days on the AIP YouTube channel, as are the previous talks. And I'd just like to thank you all, and thanks, Sougato, once again. Thanks, mate.
Thank you.